Hello friends, welcome to my channel. This is quick review of heat transfer part 3 for Isro 2017 examination. Newton's law of cooling, Q dot equal to HAS Ts minus T infinity. H is convective heat transfer coefficient, AS is area exposed to heat transfer, Ts is surface temperature, T infinity is fluid temperature. Convective heat transfer coefficient unit also important, watt per meter square Kelvin. And H is not a property of fluid. It depends on different factors, nature of fluid flow, geometry of surface, like that some factors are there, it depends. Then different states and value of heat transfer, convective heat transfer coefficient. For free convection in gas, its value is 3 to 25 watt per meter square Kelvin. And for forced convection in gas, its value is 25 to 400. And for conduction heat transfer, its value is 3000 to 25,000. And for boiling heat transfer, H value is 5000 to 50,000. These two are very important for all exams. Forced convection and free convection. In forced convection, Nusselt number is a function of Reynolds number and Prandtl number. And in free convection, Nusselt number is a function of Grashof number and Prandtl number. Or it's a function of Rayleigh number. Free convection, Nusselt number is a function of Rayleigh number also. For Nusselt number, Reynolds number, Prandtl number and Rayleigh number, Grashof number, you can check it from my playlist. One separate video I made for the important numbers, that you can check for the definitions. Then Prandtl number. Prandtl number is mu Cp by K. Momentum diffusivity by thermal diffusivity. Or we can write Prandtl number equal to delta by delta T whole cube, or delta by delta T equal to PR to the power 1 by 3. Delta is thickness of boundary layer and delta T is the thickness of thermal boundary layer. It's thermal diffusivity, momentum diffusivity by thermal diffusivity. This is kinematic viscosity divided by thermal diffusivity. And if Prandtl number is less than 1, the three conditions are very important. If Prandtl number is less than 1, then thermal boundary layer thickness is less than velocity boundary layer thickness, and kinematic viscosity is less than thermal diffusivity. In second case, if Prandtl number is equal to 1, then delta equal to delta T, and kinematic viscosity equal to thermal diffusivity. And if third case, Prandtl number is greater than 1, delta is greater than delta T, velocity boundary layer thickness is greater than thermal boundary layer thickness, and kinematic viscosity is greater than thermal diffusivity. Then relationship between local and average convection coefficient. H bar equal to 1 by AS integration of H dAs, and for flat plate H bar equal to 1 by L 0 to L H dx. Then fully developed turbulent flow inside the tube formula is here. Nusselt number equal to 0.023, RE to the power 0.8 and PR to the power n. So two things you have to remember. N equal to 0.4 for fluid heating. And N equal to 0.3 for fluid cooling. For fully developed laminar flow inside the tubes, constant wall heat flux, Nusselt number, average Nusselt number equal to 4.364, and for constant surface temperature, average Nusselt number equal to 3.66. This one once asked in IES exam. So they may ask this one also. Constant wall heat flux and constant surface temperature. Then log mean temperature difference, LMTD. LMTD equal to delta T1 minus delta T2 divided by log ln you take delta T1 by delta T2. For parallel flow heat exchanger, delta T1 is delta THI minus delta TCI. This is hot fluid inlet temperature and this is cold fluid inlet temperature. This is hot fluid exit temperature, this one cold fluid exit temperature, and delta 2 equal to THE minus TCE, difference between these two. And for counter flow heat exchanger, delta T1 equal to THI minus TCE and delta T2 equal to THE minus TCI. Then number of transfer units, NTU. NTU formula is UA MC minimum. Heat capacity, MC is heat capacity. Mass into specific heat. Then effectiveness equal to actual heat transfer divided by maximum possible heat transfer. Q actual by Q maximum. Then effectiveness formula. These formulas are very important for all examinations. Effectiveness for parallel flow equal to 1 minus e to the power minus NTU into 1 plus C divided by 1 plus C. And for counter flow, effectiveness equal to 1 minus e to the power minus NTU into 1 minus C divided by 1 minus C into e to the power minus NTU into 1 minus C. And C is heat capacity ratio. It's C minimum by C maximum. And for gas turbine, C equal to C minimum by C maximum. Its value is 1. For parallel flow heat exchanger, effectiveness equal to 1 minus e to the power minus 2 NTU by 2. And for counter flow heat exchanger, effectiveness equal to NTU plus 1 plus NTU. This is most important. For counter flow heat exchanger, effectiveness equal to NTU by 1 plus NTU. And for boiling and condensation, C equal to 0. Because C maximum is infinity, so C equal to 0. Effectiveness value is 1 minus e to the power minus NTU. Thank you friends. Thank you for watching my video. Thank you.